Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. And in this video, we're going to be looking at Chapter 2, and we're going to be considering other ways that we can represent data for pure compounds. In our previous video, we had looked at pressure versus temperature diagrams and defined vaporization and sublimation and fusion curves, the critical point and the triple point. And we had looked at pressure versus volume and temperature versus volume curves. And we had the saturation dome, which is where the liquid and vapor coexist. It's like a boiling mixture. And we have the saturated liquid line and the saturated vapor line that separate us from the compressed liquid and the superheated vapor. The peak of this dome is the critical point. So how else can we represent this? We are wanting to represent graphs of all of our properties, not just pressure, volume, and temperature. So let's do a brief review of what these properties are. These are our most common intensive and extensive properties. Recall we have volume, which for extensive we designate with the letter V, and for the specific volume we're going to put a hat on it basically, and that those units are meters cubed per kilogram for the intensive version and just meters cubed for the extensive. Density is the reciprocal of this, so its units are kilogram per cubic meter, and the extensive version of this is simply our mass. Then we have enthalpy, internal energy, and entropy. Now we have seen internal energy before. That is designated as a U, and with a little hat on it when we mean intensive. Enthalpy is designated with a letter H, and entropy with a letter S. And we will be discussing what these actually mean later, but they are all forms of energy, similar to internal energy, and entropy is going to be associated with the second law. It's not exactly an energy. We'll describe it when we get there. We also have intensive properties, temperature and pressure, and we could have kinetic energy and potential energy. And this is our complete set of properties. If we wanted to do these in a molar sense, per mole instead of per gram or kilogram, we would use an underscore to represent the molar volume, molar enthalpy, molar internal energy, and molar entropy. I have selected some various thermodynamic property diagrams from a variety of sources, simply so that you can take a look at different ways that they are presented and additional information that you might get from these. Now this first one has several differences to it. First is that the vertical axis is the natural log of pressure. The reason they did natural log is to adjust the scale. And enthalpy is our horizontal axis. Now this shows, if you can just ignore the solid stuff right now, we have our liquid region, and we have our vapor region, and we have our saturation dome in here, right? So it's sort of the same as what we've had before, but it also then goes into formation of solids. And so this diagram becomes more complex because it includes solids. This graph does not include solids. It's liquids only. It's pressure versus temperature. Oh, that's wrong up here. That's a temperature. So pressure here, temperature here. And again, we see the saturation dome. So it's saturated liquid on this side. These are compressed liquids over here. Saturated vapor over here. This is going to be our superheated vapor on this side. And this is our boiling mixture. And it's got all these extra lines on here which are going to show us values for constant values of S. So these very steep lines are constant values of S. And then I have ones that have constant value of, let's see, those are pressure, no, those are enthalpies, yes. Okay, and lots of information on here, okay? But pressure I'll read straight across, temperature I'll read straight up and down. This is a pH diagram for a different material. This is a refrigerant, HFC 134A. You probably have that in a refrigerator or air conditioner that you know and love. Very similar, okay? But this one is going to, you know, have a little bit of a different shape to it, but it's the same information, pressure. And this is enthalpy here, and this is done for constant values of temperature as we go across those, and constant values of S going up these curves along that way. Some graphs are going to show temperature versus entropy. And again, this one also shows us for a solid, but it's all the same basic thing. So we're always going to see the saturation dome. When I see that, I recognize that that's going to be my liquid and vapor region. I'm going to have compressed liquids on this side, superheated vapor on this side, and saturated in between. The peak is going to be that critical point. When they graph H versus S, that one is sometimes called a Mollier diagram. And it's, again, has all that same information, but it's kind of really stretched and skewed in a funny way, right? We, again, have our saturation dome. My liquids are over here. My vapors are over here. So this is going to be superheated vapor. This is going to be a compressed liquid. In between is the saturated liquid vapor mixture. And again, this one includes solids. But sometimes we would rather have our data presented as a table. And these tend to be generically called steam tables, even though it's not just for steam. Thermodynamic property tables is a more appropriate name. In our textbook, this is going to be found in Appendix A. The saturated steam tables come first in the organization. This is Table A1, organized by pressure, and Table A2 is the saturated steam tables organized by temperature. The superheated steam tables follow that. That's going to be Table A3, and these are organized by pressure, and then for each pressure, they're sorted by temperature. And then we have for water, we have a compressed liquid table, which is Table A4 in our textbook. Okay, it's organized just the same way, by pressure, and for each pressure sorted by temperature. Okay, now this data is not going to include every possible temperature and pressure combination, and so when we need a data point that isn't exactly an entry in the table, we're going to need to find the nearest points and use interpolation. This is covered in our textbook in Appendix B1, and we'll talk about it when we get there. There are also ways that this is going to be presented. Well, they take these tables and have set them to computer codes that are going to do all of that interpolation for you. The NIST Chemistry Webbook is probably the best source for this. It's webbook.nist.gov, chemistry/fluid. And this has 74 common substances, so steam and others. I actually have an app on my phone that will get data for me, and I invite you to explore other ways. But we need to learn how to use the tables, partly because we learn more about the relationships of properties when we have to do it the old-fashioned way. So let's briefly look at the tables. This is the saturated steam table, so notice that the pressures are lined up in order, right? So as you go through these, they're all lined up as increasing pressure. The temperature is also increasing, but they're not clean, pretty entries, right? So if you happen to have a temperature of 43.76, this would be a useful line, but otherwise a pressure is more likely to be something that you might fix and hold at one of these values. And then we have, reading across the top, we have the specific volume of the liquid, saturated liquid, and the specific volume of the saturated vapor. We also have this for internal energy, enthalpy, and entropy. The L meaning saturated liquid and the V meaning saturated vapor. When you move to the superheated or the condensed liquid or compressed liquid tables, I said they were sorted by pressure. So this pressure applies to everything below this, and then they're sorted by pressure below that. The first entry is going to be the saturation pressure at that pressure, or the saturation temperature at that pressure, and then increasing temperatures from that with the volume, internal energy, enthalpy, and entropy for each one of those temperatures at that pressure. And then the next entry is going to be over here, and all of these, they start with a saturation at that pressure and increase the temperature. Notice at 50, there's a blank here because it's not a steam then, right? The saturation temperature is 81.317, so there is no vapor at 50 degrees C. So this is an overview of our 3 basic diagrams. So that concludes this video lesson. We're going to come back and do a deeper dive into using the steam tables in our next lesson. Thank you very much for your time.